A manufacturer uses a machine to make metal rods. The length of a metal rod, L, is normally distributed with a mean of 8 and a standard deviation of x. So we can write that down. L is normally distributed 8 and x squared, because remember the parameter here is the variance, which is the square of the standard deviation. Given that the proportion of metal rods less than 7.902 centimeters in length is 2.5%, we want to show that x is 0.05 to 2 decimal places. Well, let's consider that this is the standard normal. And what we want is the z-score here when this area is 2.5% or 0.025 as a decimal. So what we can do is look in our table of values, and this is the one that we want here. And we're looking for the 0.025 value, and the z-score for that is 1.96, which means when it's on the left here, remember 0 is here, that is going to be negative 1.96. So let's standardize using what we know. The actual score is 7.902. The mean is 8. The standard deviation is x, and that's got to be equal to negative 1.96. So that gives us negative 0.098 is equal to negative 1.96x. The negative 0.098 is 7.902 take away 8. And therefore x is going to be negative 0.098 divided by negative 1.96, which is 0.05 as required. Then in part B, we're asked to calculate the proportion of metal rods that are between 7.94 and 8.09 in length. Well, we now know that L is a normal distribution with mean 8 and variance 0.05 squared. And we want to calculate the probability that L is between 7.94 and 8.09. And we can do that on the calculator. It's going to give us 0.8490. So moving on. We're now told the cost of producing a single metal rod is 20p. A metal rod where L is less than 7.94 is sold for scrap for 5p. If L is between 7.94 and 8.09, which is the one that we've just worked out, we sell those for 50p. When L is more than 8.09, it's shortened for an extra cost of 10p and then sold for 50p. We want to calculate the expected profit per 500 of the metal rods, giving our answer to the nearest pound. So, what we'd like to know first is the probability of L being less than 7.94. Again, we can get that from the calculator, and that is 0.1151. And pooling those results, we have L being less than 7.94. The probability is 0.1151. For L to be between 7.94 and 8.09 is 0.8490. And then the probability of L being greater than 8.09 is 0.0359. Those values, of course, should add up to 1. So we have 500 rods produced. If we multiply that by 0.1151, we should get the number of rods that are in this category. And we know that those are sold for scrap for 5p. Then we go to the next band. That's this band just here. So of the 500, multiply that by 0.8490, and that's how many of the 500 are in that band. And we'll multiply that by 0.5 because we can sell those for 50p. Then we have the final band, which is going to be 500 times 0.0359. That's the number of rods. And for these, we make a 40p sale. That's just the difference between shorting them, which is 10, and then selling them for 50. The cost of manufacture is 500 times 0.2. If we calculate all of that, we get 122.31, and we want that to the nearest pound, which is 122. So let's move on with the question. The same manufacturer makes metal hinges in large batches. The hinges have a probability of being 0.015 of having a fault. A random sample of 200 hinges is taken from the batch, and the batch is accepted if fewer than 6 of them are faulty. The manufacturer's aim is for 95% of the batches to be accepted. Explain whether the manufacturer is likely to achieve its aim. So, what's the distribution this time? Well, it's a binomial with a fixed number of 200, that's the number being selected for testing, and the probability of success, in this case that's being faulty, is 0.015. Now, we know that the batch is accepted if fewer than 6 hinges are faulty. And since this is discrete, that's going to be the probability of x being less than or equal to 5. We can get that from the calculator, and it's 0.9176, which is approximately 91.8%. 91.8% is less than 95%. So it's really unlikely that when we do this in a long run that they're going to achieve this value. If the probability is this, as the number of batches goes up, we're likely to converge on this number rather than 95%.